Welcome back. So, I was in the process of arriving at a description of the mathematical structure called Brownian motion, which is essentially the analog, the continuous time analog of what we have the discrete random walk. I started with a single step random walk, which was represented by a single random variable x 1, where x 1 could take values plus 1 and minus 1 with equal probability, and we found that the mean of the process is 0 and the variance of the process is equal to 1. We increased the number of steps to 2, and then we found that the variance increases to 2, and so on. As we increase the number of steps, the variance also increases. Now, our objective is to arrive at the continuous time analog by decreasing the step size to the infinitesimal level. In other words, we want to take the limit that n tends to infinity. Now, as n tends to infinity, n is, please note that n is also the variance of the process which I have just outlined. So, as n tends to infinity, in other words, as we move towards the continuous time regime, the variance of the process blows up, and that makes it incompatible with the applications that we envisage to use the process for, whether they be in the world of physical sciences or financial sciences or economics for that matter. We want to model processes that have a finite variance. So, towards that objective, we rescaled our random variables that constitute the stochastic process, that constitute the random walk by as follows, as is shown here. What we did was we moved x I or rescaled x I to under root t upon n x I, and then we found that the process does not blow up. The variance of the process is proportional to or equal to rather the time of evolution. And here in this slide I have the complete set of assumptions that we have for this was the y process. Please note we call it yi. So, this is the y random walk, and the y random walk consists of the following assumptions: y n 0 is equal to 0, that is the process starts at the origin. The number of steps is equal to n, so that the layer spacing or the step size is equal to t upon n. The up and down jumps are equal to under root t upon n, because if you look at here, x I can take the values plus minus 1, where x I can take the values plus minus 1 with equal probabilities. Therefore, y I can take the values plus minus under root t upon n with equal probabilities. So, mathematically our random walk consists of, that is the y random walk. Please note, now I am talking about the y random walk. So, the y random walk consists of n independent identically distributed random variables. It is a sequence of n independent identically distributed random variables y I, where I ranges from 1 to n, where y I is equal to under root t upon n x I, and x I is distributed as follows. It can take only two discrete values. It can take the value plus 1 or the value minus 1 with equal probabilities. Correspondingly, y I can take the values. This is equivalent to saying that y I can take the values plus minus under root t upon n with equal probabilities. Okay, and the recursive relations for the y random walk are given here, and it is easily seen that it is a sum of all the constituent random variables y 1, y 2, y 3, y 4 up to y n, where n is the number of steps and t is the time length of the total time length of evolution of the process. Please note, capital T is the total time length of the evolution of the process, and n is the number of steps. So, the layer spacing or the time difference between any two steps is equal to t upon n. Right. The cardinals of the y random walk are given in this slide. The mean of the process is 0, as is seen from equation number 1. The variance of the process is equal to capital T, which is the time of evolution. So, the variance of E and T is equal to capital T, you can see here in this box, and the square of the expected value of the square of the process is equal to capital T as well, and because the mean is 0, the variance turns out to be T. Now, each yi has a mean of 0 as well, that can be easily calculated from this particular expression that we have here in the slide. Y I can take the values plus under root t upon n with probability half and minus under root t upon n with probability half. So, expected value of y I is equal to 0, and as far as the expected value of y I square is concerned, y I square is concerned, what do we have? Y I square can take the values t upon n with probability half and t upon n with probability half. So, the expected value of y n square is equal to t upon n, and the variance sigma of y I squared is equal to t upon n. So, this is also shown in this red box. This is important. This will be carried forward when we talk about applying the central limit theorem to this process. So, let us now look at a situation where we are not talking about the total time evolution of the process, but we are talking about observing the process at any intermediate time between 0 and capital T. So, small t here is any arbitrary point in time at which we make the observation on the process. Obviously, to arrive at small t with a step length of t upon n, we need how many steps? We need small t divided by t upon n number of steps, and that is equal to small n t divided by capital T. So, we are making the observation at the end of small n t upon capital T. Now, each step is modeled by a single random variable y I, first step by y 1, second step by y 2, and so on. So, n t upon capital T number of steps will be modeled by n t upon capital T number of random variables. In other words, in our case y I will move from 1, 2, 3 up to n t upon capital T. Right. When we make these substitutions, what we find is that the variance of the process, the mean remains 0, by the way, the variance of the process is equal to the time of observation, that is, it is equal to the small t. At whatever point we are making the observation, the variance of the process is equal to that length of time. This is a very important and a very significant result. Let me repeat, if small t is any arbitrary point in time between 0 and capital T, where capital T is the total time of evolution of the process, then to arrive at small t, we need to, the step needs to make, the process needs to make n small t upon capital T number of steps, and when we incorporate that into the analysis as is shown in this slide, what we find is that the mean continues to be 0. In other words, the expected value of W of t continues to be 0, but the variance of W t at time small t is equal to small t. So, that is an important result, and that is why I have highlighted it in a red box. So, to move from the above discrete version of the random walk to the continuous time version, normally called Brownian motion or formally called Brownian motion, several approaches can be adopted. We can use the central limit theorem, we can make use of the diffusion partial differential equation, and we can use the Stirling approximation. I shall confine myself due to paucity of time to the central limit theorem approach. Now, so let me first state the central limit theorem. There are many versions of the central limit theorem. I will state here the version that is relevant to us. So, let y I equal to 1, 2, 3 up to n be independent identically distributed random variables I d random variables, each with a finite mean and variance mu and sigma square. So, each y I has a mean of mu and a variance of sigma squared. Then the following expression, which is given below, is distributed as a standard normal variate. Now, let me repeat this. Let y I equal to 1, 2, 3, that is y 1, y 2, y 3 up to y n all be independent identically distributed random variables with finite mean and variance mu and sigma square. Mean is mu and variance is sigma square. Then the following expression is distributed at a standard normal variate. This z infinity, which is defined by this expression, this is distributed as n 0, comma 1. A standard normal variate is a normal variate with a mean of 0 and a variance of 1. Right. Now, the very interesting feature about the central limit theorem, which I must mention, is that we have nowhere mentioned the nature of distribution of y I need not necessarily be normally distributed. That is very fundamental. We are not concerned with the distribution of y I. It may be a rectangular distribution, it may be a binomially distributed variable, it may be a Poisson distribution, a exponential, whatever the case may be. We are not concerned with the distribution of y I. All we want is they are independent, identically distributed random variables. That is the only requirement. Of course, the finiteness of the mean and variance are also required, but as far as the distribution is concerned, as far as the variables themselves are concerned, the only thing that is mandated for application of the central limit theorem is that they should be independent, identically distributed. They should be identically distributed, but what that distribution is, is irrelevant. It may be normally distributed, it may not be normally distributed, but this quantity that we have in the box here, this quantity is distributed as the standard normal variate, that is, it is normally distributed with a mean of 0 and a variance of 1. So, the cardinal feature of the central limit theorem is that the limiting distributions invariably approaches the normal distribution irrespective of the underlying distributions of the random variables themselves. How y 1, y 2, y 3, y n are distributed is not the issue. Whatever is their distribution, so long as all the y's are identically distributed, have the same distribution, same parameters of mean and variance, this limiting quantity that I defined by z infinity will be normally distributed with a mean of 0 and a variance of 1. The only requirement is the finiteness of the mean and variances of these underlying distributions, as I mentioned just now. Brownian motion as a limiting case of scaled random walk. Now, in the limit that the number of time steps approaches infinity, that is n approaches infinity. Please note n is the number of time steps. So, n approaches infinity if we are considering the total time of evolution of the process. And there is one more thing that I must point out before we go further, that as n approaches infinity, this quantity n small t upon capital T also approaches infinity. So, the limits as far as the limits are concerned, taking the limit with n tending to infinity would give you identical results at taking the limit n t upon capital T tending to infinity, because small t upon capital T is a finite quantity, and therefore, when you multiply a finite quantity by a quantity which is approaching infinity, the result remains unchanged. The total quantity, this quantity will also approach infinity as n tends to infinity. Right. Let us continue. In the limit that the number of time steps approaches infinity, the aforesaid construction of a scaled random walk converges to a mathematical structure called Brownian motion. This is a very important name whenever we are talking about stochastic processes. Almost all stochastic processes that are of relevance either in the physical sciences or in finance or economics are modeled in terms of Brownian motion and variants of Brownian motion, that has certain well defined mathematical properties and plays a vital role, plays a cardinal role in the modeling of stochastic processes. Brownian motion is also called Wiener process. Mathematically, the y random walk consists of a sequence of independent identically distributed random variables. I have already explained that in a lot of detail. The y random walk consists of a sequence of independent identically distributed random variables. Which are those random variables? Y I with the property that the random walk is given by the expression that is given in the blue box, and x i's are of course taking the values plus minus 1 with equal probabilities, y i's are taking the values under root plus minus under root t upon n with equal probabilities, and each y I is normally is not normally distributed. Please note that it is distributed with a mean of 0 and a variance of t upon n. It is a discrete distribution. It can take only two values, plus under root t upon n and minus under root t upon n with equal probability. That means it has a mean of 0 and a variance equal to t upon n. Now, we apply the central limit theorem to this collection of y variables, where each y I is defined in terms of y I is equal to plus minus under root t upon n with probabilities equal probabilities. So, W and T is the sum of y I. We apply the central limit theorem to the sum of y I in the form that I showed you a couple of slides back. So, when we do that, what we get is, and please note the number of steps that we will talk about, we are now talking about an arbitrary point in time t between 0 and capital T, which is n t upon capital T time steps away from the origin. This corresponds to the point t on the timeline. This is the number of steps n t upon capital T, and the time elapsed from t equal to 0 is equal to small t. Because one step length or one time step is of capital T upon n. So, if you have to traverse a time of small t, the number of steps that the process will have to traverse is small t divided by capital T upon n, that is small n into small t divided by capital T, which is the quantity that I have encircled. So, n t upon capital T number of steps will give you a point which is small t away from t equal to 0 on the timeline. So, we are applying the central limit theorem using this point as the reference point, and this point is n t upon capital T number of steps away from the origin, time steps, please note this, and therefore, we will need n t upon capital T number of y variables to model the entire stochastic process from 0 to small t. Each time step has to be modeled with one random variable, because the process will undergo a transition at the end of each time step, and then the transition needs to be modeled by a random variable. So, because there will be n t upon capital T number of transition points between 0 and small t, therefore, the number of random variables y i's that we require for modeling the stochastic process is equal to n t small t upon capital T. Therefore, we use the central limit theorem with this as the reference corresponding to the time t on the timeline, small t on the timeline, and therefore, the number of variables is equal to this, and there when we use the central limit theorem, the summation will extend from 1 to n small t upon capital T, because this is the number of variables that are there in the stochastic process up to time small t, which is that small t is an arbitrary point between 0 and capital T. So, using this, what we get on simplification is that this expression that we have here is normally distributed with a mean of 0 and a variance of 1. Let us continue from this. This is what we have from the previous slide, limit n small t upon capital T tending to infinity, summation of y I upon under root t is normally distributed with a mean of 0 and a variance of 1. That gives us that the limit n small t upon capital T tending to infinity, summation from 1 to n t upon capital T, summation y I is normally distributed with a mean of 0 and a variance equal to small t. Please note this point, here the variance is 1, but as soon as you consider only the numerator, you see the stochasticity is contained in the numerator, the denominator does not contribute to the randomness, does not contribute to the stochasticity. The flow of time is deterministic, totally deterministic. So, because the flow of time is totally deterministic, when we take this to the right hand side, take this into the distribution, the variance will be multiplied by small t, and therefore, summation of small y I in the limit that y tends n t upon capital T tends to infinity is equal to small t. This entire expression is normally distributed with a mean of 0 and a variance of small t. But this expression is nothing but W n t upon capital T into of small t. And please note, in the limit, of course, I have not mentioned limit n t tending to infinity. So, I must write here limit n t tending to infinity. I can simplify this and write it as w infinity t is equal, the variance of this expression is equal to small t. I can drop out the infinity because it is understood, and I can then write it as w t has a variance of variance. Let me write down variance here, variance of w t is equal to small t. So, this is the fundamental feature of the variance, and please note the mean of the process continues to be 0, because it is a sequence of variables, each of them having a 0 mean. So, that mean of the entire process continues to be 0. This is what the process looks like. The process that I have just outlined, w t, which is in fact an abbreviation of w infinity t, this is equal to w t, looks like what you see on this slide. This is called Brownian motion. So, Brownian motion is the continuous time analog of a random walk, which is unbiased, where we start with a finite number of steps and then take the limit as the number of steps tends to infinity. So, that the step size squeezes completely and becomes infinitesimal, and we have a continuous time regime. So, let us summarize the properties of this process w t. W t is called Brownian motion, and it has the following properties. First of all, w t is continuous. You can see from this diagram, in fact, you can make out that this process is continuous, but it is nowhere differentiable. I repeat, the process is continuous. You can see here from the diagram that the lines are continuous, but the lines are so jagged that at any point you take on this particular process, at any process point, you will find that it is not differentiable, and therefore, this process is a special process where it is continuous, but nowhere differentiable. Now, the distribution of w t, as I mentioned, w t is normally distributed with a mean of 0 and a variance of small t. Distribution of increment, this is another interesting feature of this Brownian motion. If you talk about an increment of Brownian motion, that is, if you talk about say w s plus t minus w s is also normally distributed, and what is the distribution? The distribution has a mean of 0 and a variance equal to the difference of the two variances, which is t plus s minus s, and which is t. So, the increment w s plus t minus w s is distributed normally with a mean of 0 and a variance of small t, and is also independent of the history of the process up to the time s. So, whatever was the status of however the process came, whatever path it followed up to t equal to s is irrelevant for the future evolution of the process. The future evolution of the process will only depend on the point at which the process is at t equal to s. How it arrived at that particular point at which it is at t equal to s is of no relevance in determining the future trajectory of the process. So, that is the important part. This is a Markov process. That is what we call a Markov process. So, Brownian motion is a Markov process. Representation in terms of the standard normal variates z. Now, we can write the infinitesimal increment d w t as in the form of z into under root d t. I repeat, we can write the infinitesimal increment of Brownian motion d w t in the form of z under root d t. You can check from this that by taking the mean and variance of both sides, that the mean and variance of the left hand side coincide with the mean and variance of the right hand side. Mean of the left hand side, by definition, by the very definition of Brownian motion that we saw just now, is equal to 0, and the variance is equal to d t. If you look at the mean and variance of the right hand side, it is also 0, because z has this z is normally distributed with a mean of 0 and a variance of 1. Therefore, the mean and variance of under root d t into z is equal to 0, and dt, because please note dt is a non-stochastic quantity, it is a deterministic quantity, it is a number, it is a parameter, deterministic parameter. And there is another point here that I must mention, that whenever we talk about a normal distribution is completely specified by knowledge of its mean and variance. So, because the mean and variance of these two quantities on the left hand side and the right hand side of this equation are identical, it follows that the distribution is also identical. In other words, we can perfectly represent, we can exactly represent the infinitesimal increment of Brownian motion by the expression given on the right hand side in terms of the standard normal variate. Differentiability, I mentioned already, the process Wt is not differentiable at any point, it is differentiable with 0 probability, or we can say the process is nowhere differentiable with probability 1. Fractality, the Brownian motion is a fractal. What is a fractal? Let me quickly outline because of paucity of time. If you blow up the structure of Brownian motion, for example, let me go back to this structure. If you take any segment of this Brownian motion, let us say you take this segment and you blow it up under a microscope, what you will find it that the structure remains intact. This is what is a fractal. It is a self-similar evolution which we call a fractal. So, Brownian motion is a Markov process, Brownian motion is also a fractable, Brownian motion is also continuous, but Brownian motion is not differentiable. Now, we talk about Brownian motion with drift. We generalize the concept of Brownian motion. You see, the Brownian motion in itself is a very well defined mathematical object, no doubt about that, but the point is that the structure as it is can be used to model only a very limited class of processes. We need something more general than Brownian motion to model processes which have variances and which have means which are non-zero, or variances which are not exactly equal to time, but are proportional to time for that matter. For these kind of processes, what we move on to is generalized Brownian motion. The generalized Brownian motion comprises of two parts. Basically, it is a superposition of two types of motion. One is the standard Brownian motion, which also the amplitude of which can be scaled by adding a scaling factor, and the second is a drift or a trend that you can incorporate, that you can add on to this Brownian motion to further generalize it. So, let me repeat, the generalized Brownian motion consists of two parts, a non-stochastic component given by mu dt, which does not contain any randomness, which is simply showing a trend, capturing a trend or capturing a drift in the process. For example, when we model stock prices, and due to the inflationary trends which have been observed throughout history, we need a factor to incorporate the inflation, that can be done by this particular component. And then we have a stochastic component given by sigma dw. This dw is standard Brownian motion increment, and by multiplying it by sigma, what we are doing it, we are able to manipulate the amplitudes of vibrations of the Brownian motion such that we get the variance of the process gets scaled in accordance with the variance that is empirically observed for the process that we are trying to model. So, that is by incorporating a scaling factor in front of the standard Brownian motion, and we also can add on a factor of drift, that is in order to incorporate certain trend behavior of the Brownian motion. So, this particular Brownian motion is represented by this equation number that I have encircled. Let us call it equation number 1, dx is equal to mu dt plus sigma dw. Mu dt is the non-stochastic part, sigma dw is the stochastic part, sigma is the scaling factor, the factor which influences or which modulates the amplitudes of vibrations of the Brownian motion, and mu is the setting of the trend, it is the trend per unit time or the drift per unit time, and that is multiplied by the time factor to capture the full trend. So, dx is equal to mu dt plus sigma dw. What is mean? Mean of this expression must be mu dt, because mean of dw is equal to 0, expected value of dw is 0. We have done that already. What about variance? Now, mu dt will not contribute to the variance of this process. Why? Because it does not have any stochastic component, mu is a constant and dt, as I mentioned just now, is a deterministic parameter. So, mu dt will not contribute to variance, the entire variance is captured by sigma dw, and assuming that sigma is a constant, the variance becomes sigma square into the variance of dw, the variance of dw is dt. So, the total variance is equal to sigma square dt. So, let me repeat, the mean of generalized Brownian motion which is given by equation number 1 is mu dt, and the variance of this motion is given by sigma square dt. This is an example, this is an illustration of Brownian motion which has a drift component in it. You can see the upward trend clearly manifest in this diagram, and you can also see the vibrations, the stochastic or the random vibrations that are occurring around that upward trend line. So, this is a chart that shows the whatever we have discussed so far, which captures in a nutshell what the time steps are, what the scaling factors are, and what is the mean and variance of the process. So, this is for reference of the learners. I will not spend time on it. Then I briefly touch upon drift rate and variance rate. The mean change per unit time for a stochastic process is called the drift rate, that is mu in our example. The variance per unit time is called variance rate, that is sigma squared. So, from here I will continue after the break. Thank you.